Lecture 7, covariant derivative of a covariant second-order tensor. These are the components of the covariant order, in this case, second-order tensor. And attention now, okay? You see this blue one is lecture 7. Before we derived in lecture 6, this term over here is invariant. You see this tensor is invariant. Now, what I want to derive, this belongs to the dual vector space vector, okay? That's or covector. Now, just look at this figure here. This is dual space vector or covector. See, these components, they are here, okay, belong to the dual space vector. Okay? But the covariant derivative, it's here, okay, on the vector space. Okay? This I over here, okay, that will derive the covariant derivative. This I over here is I, okay, on the denominator. That's why I is, in this case, covariant. Okay. Now, we'll develop this blue one just here. Okay. Again, as we did previously in lecture 7, in lecture 6, and lecture 5 for a vector. Okay. We are doing the same analogously. We are doing the same, okay? Now expand this. This is a partial derivative, you see? This is a contravariant basis vector, okay? And this plus this derivative plus this derivative. It's quite clear, okay? No question. Now recall that by definition, okay, the partial derivative, okay, this is a covariant derivative, is minus, okay, capital gamma IR P AR. Likewise, partial of AQ respect to I is capital gamma IS Q AS. That's this relation 2. Now, substitute 2 into 1, exactly like we did previously, okay? This gives. This is the expansion here. Now, attention now, okay? I just substitute 2 into 1. This leads to these two terms over here, blue terms. You see, what I want for this be transformed, the same AQ. This is AR AQ. This AQ is ready. You see if you compare here. And this term over here, you see AP AS. Okay? Now, AP is already here. So I don't move this. Okay? That's because we use the dummy indices, okay, properties. Now, you see red and red. Then I change here. You see, on this one over here, this is red here, okay, and red. You see here and you see here, okay. I substitute R by P. Now I have AP AQ, okay. That's as we did before. This blue one here, okay, I exchange by M and M because a dummy. Likewise, this S over here and S over there. AP is ready. I will not touch here, see? Then I'll change AS, okay? AS is red, So this is red over here, okay? Now, exactly, okay? Then the blue one, Q, you see? In this case, I'll change, okay? And the AP is ready, AQ is ready. Okay, I don't substitute because it's there. You see, the color says the whole thing. Now my intention is to this APAQ, APAQ, and this is APAQ. See clearly. Then I only want the components. Okay, this is a tensor. Okay, now I want only the components TPQ. Okay, as I have simplified in this case. This is one, this was the rest of the. Now, these are the components. You just copy from here, attention now, the second row here, okay? And I put over here, and this I repeat over there. Attention, IPQ, a lower free index on the left-hand side. You see? Now, PQI, a lower 3, okay? 3 lower indices. You see here, look, IPAQ, lower indices. Now, IPAQ, lower index. This match with the left-hand side. So that's ready, okay? So these is in this case, okay, is the covariant, okay, of this tensor over here, the component of this tensor. You see the right hand side now is minus, okay? Before I got plus, in this case is minus, okay? When I expanded the components of the contravariant, okay? This term over here, okay? This term over here, if I expand, leads to the plus sign. This term over here, which is the blue one, it leads the minus sign here, okay? This will be quite important when you apply the covariant to the metric, okay? That's a very, very important. From this, we're gonna obtain the Stoffel symbols in terms of the metric. That's a very, very, very fundamental formula for this here, okay? Well, what we're going to start. But I always emphasize, we are derived for extrinsic geometry, okay? Which is applied to undergraduate, the engineer, physicist, and this mathematics, see? So this is exterior geometry, okay? And that's it.